Hello, good morning. Welcome to today's recitation class. I can see that you have gotten to the first convection part of the course. So today we are going to be solving two questions from that chapter 8 of the textbook. Okay. So this first question is question 48. For those of you who have the 5th edition, if you have the 6th edition, it's question 50 in the textbook. So the question says, consider a 25 millimeter diameter and 15-meter long smooth tube that is maintained at a constant surface temperature. Now, fluids enter the tube at 50 degrees Celsius with a mass flow rate of 0.01 kilogram per second. Determine the tube surface temperatures necessary to heat water, engine oil, and liquid mercury to the desired outlet temperature of 150 degrees Celsius. Okay. So this question we've been asked to find the tube surface temperatures necessary to heat water, engine oil, and liquid mercury to the desired outlet temperature of 150 degrees Celsius. Okay. I'm just going to write these values out and draw the figure so that we can move on from there. So it says we have a tube. Okay, and the diameter is 25 millimeters. Okay. And the length of this tube is 15 meters. We have constant surface temperature. Now the fluid going in, so T inlet is 50 degrees Celsius. And the expected T out, T exit is 150 degrees Celsius. Okay. And then we have what other value do we have here? Okay, I think we have our mass flow rate also to be 0.01 kilogram per second. Okay, so this is similar to the problem we had in the last recitation class, but this time we just have to apply the same analysis that we did last time with the hydrodynamic boundary layer. But this time we are going to look at it in a tube. Okay, we have a forced convection problem. Now, the concept of hydrodynamic and thermal boundary layer that we used last time can be extended to this analysis. So when the fluid enters the tube, the 15-meter long tube, just like we had in the hydrodynamic boundary layer, we have a hypothetical boundary surface which divides the flow in the pipe into two regions. Okay, we have the boundary region and which we are going to consider, and then we have the irrotational flow region. This is where friction is negligible and where velocity is essentially constant, especially in the radial direction. And the thickness of the boundary layer increases as the flow moves on in the pipe. So let's say we have a pipe like this. Now, in the initial analysis, I wouldn't have drawn this when we're considering flow on the plate. Okay, I wouldn't have drawn this. I'll just consider just a flat plate. But now we have a flow in the pipe. So we assume that the flow starts to build, right? And then this is a section where we consider the flow to be laminate, okay, where we have the no slip condition. And then it starts to transition until it gets to a point where um, it has fully developed, both uh, considering the velocity and the thermal conditions of the fluid. So because it's in a pipe, you have something like this also. It's almost symmetrical. So you have this imaginary line, okay? So the thickness of the uh, fluid at any point in time we can call delta, right? Just like we did when we're analyzing flow on a flat plate. Okay. So as the flow moves on, it becomes fully developed at some point in this pipe. Now the length from the point of entrance to the point where it gets fully developed is what we call the hydrodynamic entry length. Okay, hydrodynamic entry length. Now, this same analysis can also be applied to the thermal conditions of the fluid, and we'll also be looking for a thermal entry length. Okay, and we have a formula for these two conditions. These are useful in when we are trying to find um, um, the length for which the fluid is still developing, because as you can tell from fluid, once it develops, the velocity and thermal conditions don't change very much. Okay, so we are concerned with the length which it is still developing. So from your textbook, I'm sure you must have seen these two formula. We have the length for the hydrodynamic entry region for laminar flow to be approximately 0.05 Reynolds number multiplied by the diameter. And then that for the thermal entry length for laminar flow is approximately 0.05 Reynolds number diameter multiplied by Prandtl number. So it's basically just the hydrodynamic length multiplied by Prandtl number. Okay. So now we can use this expression to find the length that we're interested in. But from this, we have a special type of flow. This is laminar flow in a circular pipe with constant temperature on the outside. And I'm sure you can also find this from your textbook that the Reynolds number for this condition is 4 multiplied by the mass flow rate divided by pi diameter and dynamic viscosity. So we can use this expression to find our Reynolds number. We already know what the diameter is. We can find the Prandtl number from table of properties. Now, this hypothetical boundary layer that we're considering exists somewhere in our tube, but we can't tell exactly where it is, but we can approximate it. Okay, and we can do that by finding the bulk mean temperature, right? And T subscript B is just the arithmetic mean of the inlet and exit temperatures. That's Ti plus Te divided by 2. And we have been given this to be 50 and 150. So I'll just say 50 plus 150 over 2. This gives me 100 degrees Celsius. Okay, that is our arithmetic mean temperature that we're going to be using. Okay. So now from the tables of the table of properties, we can find the values that we need to do our analysis. Now we want to find. We're not doing this just for one fluid. We're going to do this for water, engine oil, and liquid mercury. So I'm just going to draw a table here just to have a clean, just so we can see all the values that we're coming up with. So I'm just going to draw a table, say fluid, I have water, um, engine oil, and liquid mercury. Okay. So as we get the properties, we just write them down. So the first, so we need to find specific heats. We need to find the thermal conductivities. We need to find dynamic viscosities, and we also have to find Prandtl numbers for these different fluids because we're going to be using them in our solution. Just tabulate them and so we can easily just pick them out. So from your textbook, I don't know if I'm using the 6th edition, and for water, you find the properties for water at liquid water at 100 degrees Celsius in table A9. Okay. And I already pulled out those properties. So I'll say the specific heat. The next thing is thermal conductivity. And then we have dynamic viscosity and Prandtl number. So for water, we have for, now these, I'm not going to write down the units because I'll just write them up here. Joules per kilogram Kelvin. And then we have watts per meter Kelvin per kilogram per meter per second. And then this is just a ratio. Okay, so for water, we have 4,217. 2,000. Now these are from the tables, okay? I'm not just coming up with numbers. These are the values for these fluids at 100 degrees Celsius, okay? You might have to check each one. I think for engine oil is table A13, and then for liquid mercury is table A14, just in case you want to check. And please let me know if I've gotten any of these values wrongly. And then this is 282 times 10 raised to the power minus 3. Okay, the Prandtl number, this is 1.75279.1 and 0.0180. Okay, so now we have our properties. We can go ahead and compute the Reynolds number for each of these fluids, and then subsequently compute the hydrodynamic and thermal entry lengths. Okay, so Rate number for water is 4 times. We have a constant we have a mass flow rate that applies to all the fluids, which is 0.01 kilograms per second, and just divided by pi. We have a constant diameter too, 0.25. Just convert that quickly to meters. Just divide by 1,000 meters, and then multiply by the dynamic viscosity. For water, we have that to be 0.282 times 10 raised to the power minus 3. Okay. Now, if we compute this, we'll get this value to be 1,806. Okay. Now, in the same way, compute this for engine oil. And we also get this one to be 29.64. And then for liquid mercury, okay, 4 times 0.01 kilograms per second. Times 1.245. And then we get this to be 409.1. Okay, so I'm just going to go ahead and impute these values also. So the Reynolds number for these three, 1806, 29.64, and 409.1.
Vincent, do you want to scroll down so we can see the whole
Oh,
form?
I'm sorry. You see that. Okay. So we have the Reynolds numbers for the three fluids. So some of these calculations are just procedural. You just have to follow it step by step. So I'm just going to skip them so that we can have enough time to run through the other question. So we have this value. All we have to do now is just impute the Reynolds number in this expression, right? We also have Prandtl number from the tables. So if you impute those values, we can get the expressions for the length for entry length for the hydrodynamic entry length and the thermal entry length. Okay. So if we do that, you get these values to be, I'll just write them down and then you can try and do it on your own just to make sure we don't have any mistakes. Okay. So for water, we have 2.258. We have 0.03706, 0.5113, 3.951, 10.34, 0.009204. Okay, now this is the reason why I wanted us to tabulate this, because you have to look at the values and do some analysis. Okay, now for laminar flow in a pipe, in a circular pipe, we know that if the Reynolds number is less than 2,300, then the fluid is still in its developing stage. Okay, as long as it hasn't gotten to this value, then it's still building out. So if we take a look at the Reynolds numbers for the three fluids, they are all less than 2,300. So it means that and within the length of our 15-meter long tube, the fluid is still developing. It hasn't gotten to that point where velocity and thermal properties remain kind of constant. Okay, so which is good. We just have to consider the laminar side of fluids. Okay, and also if you look at the entry length for our three fluids, both hydrodynamically and thermally, looking at both of them, they are all going to fully um, develop inside the tube because they are all less than 15 meters in length. Okay, this is in meters. Okay, so this makes it kind of straightforward and simple because we have an Nusselt number for laminar flow in a constant surface temperature circular pipe. We have a value for that. So finding the convective heat transfer coefficients for our fluids should be very simple. So we have the expression H is equal to thermal conductivity divided by the diameter multiplied by Nusselt number. And we've been given a circular pipe with constant surface temperature. We have that value to be 3.66 for this condition. Now, if we had gotten different values here, then we might have had to compute Nusselt number. There are values you would get here that will make you not use this. Okay, we're only using this because the conditions that we have evaluated now, this is what fits those conditions. Okay. So in the same way as I have computed this, you go ahead and compute the we know the thermal conductivities for all our fluids. We have a constant diameter, so we can find we have a constant Nusselt number, so we can go ahead and find the convection heat transfer coefficients for free fluids. Now, once again, I'm just going to go ahead and put the values that I have already computed down. Okay. So this will just be a continuation of this table. I've run out of space, so I'll just continue this table down here. So I'll say water, engine oil, and liquid mercury. Okay. So the H values for these three, H is watts per meter Kelvin. Here we get 99.4, and then we have 20. And for this, we have 1,390. Okay. So the question, we now have everything we need to be able to evaluate the temperature with which the individual fluids exit the tube. Okay. We can find that by using this formula. Now we have a formula for the formula that determines the exit temperature for a circular tube with constant surface temperature. This is from your textbook also. Is there any questions so far? I hope all these are not new to you. I hope they don't look very strange. So in this formula, TE is the exit temperature. This is this constant surface temperature that we're looking for. Okay, this is T inlet. This is the individual convection coefficients, heat transfer coefficients. This is a constant surface area, which is constant also. This is a mass flow rate. This applies to all the fluids. And then this is the individual specific heat for the fluids under consideration. Okay. So if we rearrange this equation, because we're trying to find the constant surface temperature, we know every other thing here. We get Ts is equal to this expression. Oops. Okay, so this expression gives us the constant surface temperatures for the fluids. Okay, this is the temperature that you have to. What we're basically doing in this question is we're designing a heater. Okay, this is the temperature that you have to maintain on the outside of the walls of the tube to ensure that the fluids exit the tube at this temperature. Okay, so once again, if you compute this, you arrive at these values. Okay, you have one. So, I'll just see. Okay, so T surface. Okay, and this is in degrees Celsius. So for water, you have 157. For engine oil, you have 207. And for liquid mercury, you have 150 degrees. Okay, so this is your final answer. Now, there's a comment I want to make here. Do you notice something about these values? Okay, you have water at 99.4 watts per meter Kelvin. You have engine oil at 20, and then just take a look at how huge this value is. 1,390 for liquid mercury. Okay. So this is a very valuable property for this is useful for applications where you want to there's a need to get rid of a lot of thermal energy in a short period or which in a small space of time. This is a huge convection heat transfer coefficient. Okay, liquid mercury will be an ideal um, fluid for that application. Okay, is there any questions so far?
I have a question.
Okay.
So, Vincent, do a lot of liquid metals have a pretty high H value?
Um, no, not really. Not many of them have that property. No.
So, liquid mercury is just kind of special.
Yeah. If you must have seen videos on YouTube or online about the cohesive properties of mercury. Okay, it has very high cohesive properties. If you drop, if you put a drop of liquid mercury on this table, it just rolls off. Okay, it has special properties. Yeah, and it's pretty expensive too.
Cool. Thank you.
Yeah, you're welcome. So if there's no other question, I'll just go ahead and get to the next question. So I'm going to post the video for this class, and just in case you're solving your homework and you miss a step, or you want to go back and revise something we did in this class, you can just watch the video. Okay, so the second question is question 75. in chapter 8 for 5th edition, question 89 for the 6th edition. Okay. So it says water is to be heated from 10 degrees Celsius to 80 degrees Celsius as it flows through a 2 centimeter internal diameter, 13-meter long tube. The tube is equipped with an electric resistance heater, which provides uniform heating throughout the surface of the tube. The outer surface of the heater is well insulated, okay, so we're not losing any heat. So that in steady operation, all the heat generated in the heater is transferred to the water in the tube. If the system is to provide hot water at a rate of 5 liters per minute, determine the power rating of the resistance heater. Okay, that's question 1. Also, estimate the inner surface temperature of the pipe at the exit. Okay, that's question 2. Okay, this is another heater problem. Now, there's something I have been missing in most of the problems that I've been solving. I've always skipped the initial assumptions because I just sometimes I just forget because I assume that they are they are pretty obvious. But this is one of the problems where you have to really highlight that assumption. Okay. And the assumption that makes solving this question simple is that there's uniform surface heat flux. Okay, the heat being supplied to this tube is uniform throughout. That makes it easy to compute that exit temperature. Okay, so in this question, we want to evaluate a system where water is to be heated in a tube that has an electric resistance. Let me draw the tube. Okay, we have this. We have the inner diameter, 2 centimeters. The inlet Ti is 10 degrees Celsius, and T out is 80 degrees Celsius. Once again, we have constant surface temperature. The length of our pipe is 13 meters. What else? This time we have a volumetric flow rate, which is 5 liters per minute. Okay. Let me write out. Okay, we already have these values. Once again, we are going to be doing our analysis at our boundary layer. We have to take an arithmetic mean of the temperature coming in and going out and assume that to be our boundary layer. Okay. So the bulk mean temperature is Ti is Te divided by 2. And this is 10 plus 80 degrees Celsius divided by 2. This gives us 90 divided by 2, 45 degrees Celsius. So we're going to be working at this mean temperature. So once again, this time it's a lot easier for us. We're working with one fluid, just water. So if you go to table A9, table A9, you can pull out the values that we need. Okay. So I'm just going to write down those values. I already have them with me. Density. meter cube. Thermal conductivity is 0.637. We have the dynamic viscosity. Let's pull that out. This is 0.596. Okay. And the specific heat at that temperature is 418 joules per kilogram Celsius. And Prandtl number is 3.91. Okay. All right. So the first thing we can do is it is asking us to find the power rating of the resistance heater. And that is a pretty straightforward one because we know that the power in the circuit is just can be found by using this expression. It's just the amount of energy transferred into the fluid. And you can find that by just finding the temperature difference from one end to the other, and then the mass flow rate and the specific heat. You find the amount of power needed to do that. Okay. So we don't have a value for this, but we can find the mass flow rate by using the volumetric flow rate. Okay, mass flow rate is simply the volumetric flow rate multiplied by the density of the fluid, right? Okay, so we have been given the volumetric flow rate in liters per minute, and that is not a standard value. We have to convert that into kilograms into meter cube per second. Okay, and I think 1 liter is equal to 1,000 cubic centimeters. So to convert this, you just divide the value by 1,000 to get the equivalent value in meter cube. Okay, and then divide by 60 to find the value. So the standard value should be meter cube per second. Okay, that is the standard value. So we're going to divide 5 by 1,000 and then divide by 60 to convert it to seconds. So that is 0.005 meter cube divided by 60 seconds. That is our standard value. And we have our value for rho to be 990.1 kilogram per meter cube. See that meter cube, these two are going to cancel out, and then you have kilograms per second, which is the value, which is the standard value for mass flow rate. Okay. So if you compute this, we'll get I think I wrote that down. We'll get 0.00083 meter cube per second. So this is 0.0004083 meter cube per second multiplied by 990. 990.1 kilogram per meter cube. Okay. And if you evaluate this, we get our mass flow rate to be 0.0825 kilograms per second. Okay. So we can now put this in our equation here to find the power that is needed to for the amount of energy that will be transferred into the fluid. So Q is equal to 0.0825 kilograms per second multiplied by the specific heat we have to be 4180 joules per kilogram degree Celsius. And then remember, this is just a temperature difference, so no need to convert it. Just we can use a 80 minus 10 right away. Okay. And if you compute this, you're going to get 24,140 watts. So it's a 24 kilowatt heater. Okay. So we have the first part of the question, which was pretty straightforward. The second part of the question is asking us to find the inner surface temperature on the inner part at this point of the heater, where the water is exiting the heater. Now, we should also find the Reynolds number and the velocity at that point to be able to understand the nature of the fluid at that point, because that would determine the Nusselt number that we're going to use, and also to also tell us what is going on at that point. Okay, and the Reynolds number for this type of question is given by the average velocity divided by the diameter and hold on, I need to check this. Um, yeah, divided by V. Okay. Okay, and we need to find the average velocity. We also have an expression for that. Okay, from your textbook, you see that the average velocity is the volumetric rate divided by area contact. Okay, this is a formula from your textbook. Okay, I'm just pulling it out from there. Okay, and we know this to be 5 liters per minute. We already converted that to standard units. Okay, and we know the diameter of the tube, so we can find the area. Okay, so the V average is now equal to, we have this value to be 0.0008883 meter cube per second divided by area, which is going to be pi multiplied by, so 2 centimeters, just divide by 100 to get the standard unit. So that's pi into 0.02 square. Okay, this is in meters, and then divide this by 4. Okay, and so we get a V average to be 0.2653 meter per second. Okay, and also we can get a V by dividing uh, dynamic viscosity by the density. Okay, so this is equal to over rho. And we have this from the tables, some of the values are pulled out of our table to be 0.596 times 10 raised to the power minus 3. Okay. All this divided by our density, which is 990.1 kilogram per meter cube. So I hope all this makes sense so far. This is kilogram per meter second. Okay, so we get this to be 0.602 times 10 raised to the power minus 6 meters squared per second. Okay, so we can now compute the Reynolds number for this fluid at this point, right? We get this to be 0.2653 8,813, which is way greater than 2,300, right? So at this point, our fluid has fully developed. It's way past the transition stage, and no, it's in the transition stage because it's still less than 10,000. Because this is the point where we know it has fully achieved turbulence. So it is in that transition stage. Well, it's close to 10,000, okay? So which is, we can take this to be turbulent at this point, okay? Okay, so we can assume that this is turbulent. We can do a quick test just to see, okay? We can use this expression just to do a quick test and see that if we assume that these all happen at the same region, and we know that this is going to be close to this value, okay? And we know we already got our diameter to be 0.02 meters. If you multiply 0.02 meters by 10, you get 0.2 meters. Okay, this is way shorter than the length of the tube that we're working with. So we can just go ahead and assume that it has fully developed turbulence at this point. Okay, so we can use the Nusselt number formula. We can't assume the Nusselt number to be 3.66 anymore. We have to use the Nusselt number formula to find what the value would be at this point. And this is the formula that we can use to find that. Okay. I hope this makes sense so far. Okay. So from your textbook, this is equivalent to 0.023 Reynolds number raised to power 0.8. And then we'll multiply this by the Prandtl number, which is 0.4. We have this, and we also have this, right, from our tables. If you evaluate this, you get a Nusselt number to be 56.85. Okay. Now, once we get this value, we can also compute our convection heat transfer coefficient. We have H to be K multiplied by Nusselt number divided by pH. Oops. We also have everything we need here to compute this value. Okay, we already have our K value. We should pull that off the table. Okay. 0.637, 56.85. All this now divided by 0.02 meters, which is our diameter. I will get our H to be 1,811 watts square degrees Celsius. So we know what the convection heat transfer coefficient is at that point. So it becomes a simple Fourier's law equation problem now, okay, to find the value of T at that point. So, and if you, we call this so is the surface temperature at a point of interest, I'll just call it X, okay, minus the exit temperature, just the difference between that short distance. Okay, we know the exit temperature and we've evaluated the convection heat transfer coefficient at that point. We know what the area is, and we also know what the power is that is being delivered to our system. Okay, so we just equate this and pull this out, and then we can find our value. So that's 24,140 watts is equal to 1,811 degrees Celsius. So the area is pi multiplied, we already computed this earlier, but I'll just write it here again, 0.2 meters square. Oh, hold on, I'm just going to compute. So the distance, remember when I said the hydrodynamic length, right, is the point of entry to the point where we, in this case, we were talking about the point where it is fully developed. But in this calculation, we're looking at the point of entry to the point of interest, okay? And our point of interest is just before the exit, okay, which is we can take to be 13 meters into the pipe. Okay, so our surface area is the entire length up to that point. Okay, so it's the internal surface area. So I'm just going to multiply this by 13. That gives me the perimeter. This is just perimeter multiplied by x. I'm sure you must have done this in classes. Okay. The perimeter multiplied by x gives me the total internal surface area to the point of interest.
Hey, Vincent. Oh, never mind. We can see it.
What? Oh. Okay. Can you see it now?
Yeah, thank you.
Okay. Sorry about that. And then Tx, which is our point of interest, Ts, x minus our exit temperature. Let me just write this, 80 degrees Celsius. Okay. So if you evaluate this now, we'll get Ts at x to be equal to 96.3 degrees Celsius. Okay. So that's our answer. Well, out of time, but I just want to quickly make a correction. In the last recitation class, if you remember, I ran into trouble with the last question. The question that had to do with the metal plates in an oven. I don't know if you remember that. And I made a mistake with that question. Okay, I pulled out the wrong solution and I didn't cross-check before the class. So that question, let me just, I think it's question. So it's question 17 in chapter 4, which says metal plates with a thickness of 1 cm are being heated in an oven for 2 minutes. Air in the oven is maintained at 800 degrees Celsius with a convection heat transfer coefficient of 200. And if the initial temperature is 20, determine the temperature of the plates when they are removed from the oven. Now, in that question, what we were supposed to do was to, first of all, find out if the Biot um, the Biot number method, which is used in sub-lumped system questions, was applicable. Okay, and there's a simple formula for that. You just find the let me see if I can share the screen with you just to show you real quick. Okay, let me just share the screen with you quickly. Okay, so in chapter 4, when you do when you consider a problem, a transient conduction problem, and you make the assumption that there's a uniform distribution of heat around the material, especially for materials that have weird geometric shapes. Okay, in order to make that assumption, you have to first of all evaluate using the Biot number. Okay, and you can do that by first of all finding the characteristic length. So in that question, I think this is what I was trying to evaluate that day, and I was wondering where in the solution the values had come from. So there's a half thickness length assumption, which is where you say 2L is equal to the thickness that you've been given. So you can find the, the value of L. And if you get a value that is less than 1, okay, if you get a value that is a Biot value that is less than 0.1, then you can use the lumped system method. Okay, this is a similar example to the one that we're trying to solve. It says here that metal plates, given the values with a thickness of 2 cm, exiting an oven. This is a similar question to that one. Okay, and then you come here and then you do the test by making this analysis. So you have 2L is equal to 2 cm. You find your value of L, and then you have this value, and then you put it in the Biot equation, okay, just to find if the value is less than 0.1. If it is less than 0.1, then you can go ahead and use this method. Okay. So once again, sorry that I made a mistake in the last class. Just wanted to make that correction. So is there any question? I hope I've been able to help with questions. So if there's no question, I think the professor sent out an email saying that today's class is canceled. So just say have a nice rest of your day, and you can always send me an email later on if you have any other problems. Okay. So have a nice rest of your day, guys. See you next week.
Thank you. See ya.
Yeah.